Hello, in this video, we're going to continue talking about gravitational potential and some other HL gravity stuff. So here's a quick recap of what we talked about a little bit so far. Gravitational potential is this new kind of unit that we measure in joules per kilogram. You really want to think of it as energy per unit mass. The units here will really help guide you on what it is. Of course, the units don't make an equation. You need the data booklet equations to find numbers for these. But the units will really help you conceptually think about what they are. Field strength, remember, is kind of measured in newtons per kilogram, and you can think of it as a force per unit mass. So these are two ways to represent what's going on around something like a planet, independent of however much mass I actually put there. So those are the two ideas we've talked about so far. Okay, a couple other equations that come up. Again, the derivation of a lot of these is on Cognity, if you care to look. I'm not going to get too into the derivation. We'll talk more practically about how to use these equations. But you're going to see graphs that look like this. They're graphs of potential versus distance. And if we think about the equation for gravitational potential, negative g times big M over r, it hopefully makes sense that this equation will look, the graph of this equation will look like this. It's a basically negative 1 over x graph. Here's another data booklet equation that tells us something we can do with this graph. So this equation says little g, the vector, is equal to negative delta vg over delta r. You want to recognize anytime you see an equation of this format, delta over delta, that represents a gradient. That represents, the steepness of the graph, the slope of a line tangent to that graph. And so the gradient of this graph, potential versus r, is equal to field strength. Okay. This is another graph you basically want to memorize. It's like seeing a force time graph and going, ooh, yes, okay, I know what to do. I take the area under the curve. I set that equal to the impulse. Same thing here. If you see a potential versus distance graph, the thing you do is you find the gradient. You're going to draw tangent lines, okay? Draw a tangent line at a point, and the steepness of the tangent line at that point tells you about the strength of the field. Now, it is negative, so imagine this is the gravitational potential graph for the Earth. We're at the surface of the Earth. I got a pretty steep potential, or a pretty steep gradient here, so I have a strong gravitational field. And the slope of this line would be positive, but we would say the field strength is negative. That represents that the field is pointing down, right? And you can imagine tracing this graph as you go, the gradient decreases in magnitude. It gets less steep, right? And so that represents, as you get further away, the gravitational field gets weaker. So that's a thing we can do with this graph that we'll practice. That's a very common paper 2 kind of thing that you will definitely see. Gravitational potential versus distance graphs. Draw a tangent line, take the slope. The size of the slope is equal to the field strength. Okay, so here's what that'll look like. Again, remember how to do this. Pick the point on the graph at the distance you care about. Maybe we care about how strong the field is at the surface, or like 2r away from the planet, or 500r away from the planet. Wherever we might be, you go to that point on R, draw a point, take your straight edge, draw a nice long line. Remember, make the line as long as you can. Pick 2 points far away because you want to get a good slope. If you pick a point here and here, your slope's not going to be as accurate probably as if you pick a point out here and out here. All right, and you find the slope, and that's your field strength. Be very careful with units here. The units are going to be usually crazy. This might be in terms of like Earth radii or something, and this is probably going to be in something like megajoules per kilogram. So just watch all your units on your graphs as always. Okay, here's a big recap of your topic 10 data booklet. The topic 10 data booklet is one of the most intimidating sections of the data booklet. You have all these different equations that are super similar to each other. I got a negative gm over r, I got a negative gmm over r, I got a regular gmm over r squared, and they're all different things, completely different things. You have to be very careful and know what all of these are. So being familiar with your data booklet is the number one thing you can do to be most successful on the IB exams. So here's these 4 quantities. Now, when we get to them, these other 4 cells have the electric equivalents of these ideas in there. So we'll get there. All right, but this first one represents potential. Remember, V is going to be potential, so that's our joules per kilogram. Thinking about the units for these will really help you make a distinction. So this will give me that potential thing in joules per kilogram. This will give me field strength. Remember, that's newtons per kilogram. All right, now this will give me potential energy, which is just joules, and this will give me the force due to gravity. That's good old lug. That'll give me newtons. Yeah, so think about how they're different, right? This is joules. This depends on 2 masses. This is joules per kilogram. independent of there's no other mass there. This is just what's going on around the big M making the field. Same thing here. This is the actual force acting between two masses that they pull on each other. Little g is sort of an abstract way to say, okay, newtons per kilogram. This is, again, just what's going on around the surface of around the planet, wherever. Newtons per kilogram. So there's no little m. Remember, we do have in topic 6 the other version of this equation, which is just g times big M over r squared. So we really, truly have every combination of g's and m's and little m's and r's. All right, so studying these and making sure you can make the distinction between them is a huge, huge part of being successful here. You have to know this stuff really well to have a shot at doing well with the topic 10 stuff. Okay, and one more equation we'll look at, which is in from 10.1, right next door to this exciting table, is very, very similar to another equation we've done. All right, it's almost the same thing. It's another way of looking at joules per kilogram, and kilograms. All right. The difference here is instead of just potential at a point, we define something called potential difference. So if things weren't exciting enough, officially there is a difference, no pun intended, between potential energy, potential, and potential difference. Those are kind of 3 separate things. Potential difference is very similar to potential. It's just the difference in 2 potentials. Whoa, mama. Okay, so this equation tells us how much work it takes to move a thing from point A to point B through a field. So all I really have to do, this is really just an application of this equation. Potential energy at a point is mass times its gravitational potential. And so, of course, if I want to find the work, I'm finding the change in energy. So we can just imagine this equation is delta EP. That's really what I'm finding. The change in potential energy is the work done. This equation just kind of factors that in, because I'm going to do the change in potential times mass. That'll give me my change in potential energy, aka the work. All right, so delta represents that change, represents a final minus initial. So of course we can do potential at the end, wherever we end up, minus potential wherever we start. One other fun thing to note is that this is the work done to move a thing through a field. So if I lift a mass, say from the surface of a planet upwards into space, I have to do positive work, because of course I have to push against gravity. So the work would be positive, and the work should come out positive in this equation if I go from the surface of a planet up to some higher point. Sometimes you might need to talk about what kind of work gravity does, though, and it's the opposite. Okay, because think about our sort of one of our formulas that helps us define work, which is force times displacement times the cosine of the angle. And when the force and the displacement are opposite, you do negative work. Well, that would be what's happening if I lift something from the surface of a planet up into space. Gravity, the force due to gravity, is down while my displacement is up, so gravity would do negative work while I do positive work to bring it up to that point and just like kind of place it there without, speeding it up or slowing it down. So this is the work done by your force to move something. Gravity always does work opposite to that in sign. Again, work being a scalar. All right, so last problem we can try. I want to send my cat, Joe, to space. I'm going to put him in a little homemade rocket. I took a water bottle, filled it up with some water. I'm going to pump it up real good and hope he can make it. Tape him to the bottle and cross my fingers. Hope he'll make it. He's a tough guy. All right, so my cat plus the rocket is 25 kilograms, and so I could figure out how much work I need to do. Well, how much work the rocket needs to do to send him to space. 100 kilometers. That's officially space. Very similar to what we did before. All right, so again, this is really the same concept, but it just kind of bakes this change into the equation. I'm going to use this formula. Work done is the mass that I am moving through the field times the potential difference that the mass moves through. So I'm going to take the mass of Joe and his rocket and multiply by the change in potential. So I'm going to do final potential. Be careful with your signs here. Final potential is negative 61.6 million joules per kilogram. And then I'm going to subtract the initial potential. So I'm going to minus a negative. And I started down here on the surface where the potential was this much. All right, so this becomes, I add it, and I end up with a positive answer. 30 million joules. So 30 million joules, that's how much energy it would take to send my cat to space. All right, this is why it's very expensive to send stuff to space, to bring something to the space station. If you want to bring your cat up to the space station with you, it'll cost you 30 million joules of energy to bring it up. and the space station's even a little higher than that. Yeah, so it takes a lot of energy to get something out of the gravity well of the planet to get it up into space because of this potential difference. That's one way we can think about what's going on here with all this potential energy stuff. All right, so these are all just ways of measuring energy, potential energy, out in space above the surface of a planet relative to some universal relative zero, which is at infinity. So some of the math that comes out of that is exciting and fun. But there you go. All right, that table in topic 10 is really helpful to study. Remember what to do with the V versus R graph. Those are the big things that come up with gravity. Things get there's a lot of other kind of similar topics that we'll talk about when we get into electric fields because they behave in very similar ways to gravitational fields. So we will get there one day soon. But for now, this is plenty of fun for you to have with gravity and all kinds of new equations. So have fun.